Okay, welcome to the inaugural meeting of the Topological Complexity Seminar of the AATRN. Before we start, let me say that this presentation is recorded, and also all microphones are set to mute by default. But if you have a burning question for the speaker, you can unmute your own microphone and ask. However, also note that after the talk, there'll be a time for questions and comments. So if possible, you can save comments or questions till then. Without further ado, I'm happy to introduce our speaker, Mark Grant of the University of Aberdeen, who will speak on Bredon cohomology and LS-categorical invariants. Take it away, Mark.
Okay, so I'm sharing my screen now, and I should be able to go to full screen. How's it looking?
Good.
Good.
Looks good. Looks good.
Okay, I need to move that part. Okay. So thank you for coming along. It's a great pleasure and an honor to be the first speaker of this seminar series, which should be a fantastic way to get together and learn about what's going on with topological complexity. So I'm going to talk, my talk has, well, 2 and a bit parts. In the first part, I'm going to report on not so recent work, which was joint with Michael, Greg, and John, in which we used Bredon cohomology to give lower and upper bounds for the topological complexity of groups. And I wanted to talk about this, well, the protagonists are all here. Also, I haven't had a chance to talk about it at many places before, but also it compares nicely with the next part of my talk, which is doing the same thing, but for the equivariant LS-category of groups with operators. So I'm going to present the work done in collaboration with some colleagues in Aberdeen, Ehud, Meir, and Patchkoria. And then I'm going to end up with some fairly speculative things which popped into my head this summer, and I haven't had much time to think about since. So part 1, Bredon cohomology and TC. Well, here's the obligatory slide, as John called it. Why are we all here? I'm going to assume that everyone here knows this definition already, so not make too much fuss about it. Topological complexity is a numerical homotopy invariant defined by Michael Farber as a topological approach to the motion planning problem in robotics. And it can be described as the sectional category of the free path vibration over x times x, which sends a path to its pair of endpoints. So we're looking for the smallest k, such that there is a cover of x times x by k+1 sets. So I'm using the normalized version of TC here, on which we have a local section or a lift through the projection of this fiber map. Now, the problem which has interested me and many people for a long time is the following. Suppose you have a discrete group pi, and you ask what is the topological complexity of a k pi 1. So a space whose fundamental group is pi and whose higher homotopy groups are all trivial. Well, we know that this is determined uniquely up to homotopy type, and therefore TC pi is an invariant of the group pi. And Michael posed the problem in a survey article which was published in 2005, described TC pi in terms of algebraic invariants or other algebraic invariants of the group pi. And this problem remains unsolved, even in conjectural form, I suppose. Really, we don't really have a conjecture about what this description should be, despite the fact that the exact value of TC pi is known for many groups or families of groups. So notable recent advances have been work of Dronichnikov and Cohen van den Broek, who are all here, I note, who calculated topological complexity of non-orientable surface groups. Dronichnikov again, who calculated topological complexity of non-abelian hyperbolic groups in the sense of Gromov. And I just noticed a preprint that came on the archive this week by Andrea Bianchi, which solves the problem for braid groups. which was an outstanding case. So we know a lot, but we don't yet have this wanted description in terms of algebra. So I need to fix the notation. E of x for a topological space X will denote the infinite join with Milnor's topology of copies of X, and it's filtered by the k+1 fold joins, which will be denoted by E sub k of X. This is functorial. In particular, if a group G acts on X, then it acts on the joins, various indices. It acts diagonally by acting on each X. And so if you have a discrete group pi, the Cartesian product pi cross pi, well, it acts on itself by left translation, left multiplication, but it also acts on a single copy of pi by this kind of left-right multiplication like this. This is a left action of pi cross pi on pi. And so we have actions of pi cross pi on the infinite join of copies of pi cross pi on E pi and on E sub k of pi. Now, the starting point of this work was the following proposition, which appears in our joint paper, but is actually due to Michael, which says that the topological complexity of the group pi is equal to the minimum k for which there exists a pi cross pi equivariant map from E pi cross pi to EK pi. Now I can give the proof of this because it's brief. I won't subject you to too many proofs, but it just uses a little bit of homotopy theory and the fact that the loop space of a k pi 1 is a discrete space. So when you look at the free path vibration for X, a k pi 1 space, you see that the fiber is homotopy equivalent to just pi viewed as a discrete space. And because the monodromy action is what it is, you can actually identify this vibration up to homotopy with the vibration with fiber pi associated to the pi cross pi action on pi that we just gave, the left-right action. And then if you think about it a bit more, you see that the k+1 fold fibered joins of this free path vibration on X, it is homotopically equivalent to the vibration with fiber, the k+1 fold join of copies of pi associated to the action of pi cross pi. And Schwarz tells us that the sectional category of a vibration is the smallest k for which the k+1 fold fibered join admits a section, and then sections of this associated vibration are in correspondence with pi cross pi maps from E pi cross pi to EK pi. So I hope that this is familiar to at least most of you. So it's not such a surprise that this should be true. But now we have a characterization of TC of a group in terms of whether or not there exists an equivariant map between spaces, so we can apply all the machinery of equivariant algebraic topology to try and answer this question. In particular, we can talk about Bredon cohomology and such things. In order to talk about that, I need to first talk about families of subgroups and orbit categories and so on. So I'm going to use gamma now to denote an arbitrary, well, I'll stick in the world of discrete groups. So gamma is an arbitrary discrete group. Curly F is a family if it's a non-empty collection of subgroups of gamma, which is closed under conjugation and taking subgroups. This is, I think, a slightly stronger definition of family than we use in our paper, where we just insist that it's closed under conjugation and finite intersections. But it makes, for me at least, it makes some of the statements I'm going to make a bit cleaner. Some kind of useful or obvious examples of families of subgroups. You could take the family consisting just of the trivial subgroup. and that will be called the trivial family. You could take the family of all subgroups of your given group. That will be called curly all. And most interesting for us is that if you take K to be any subgroup of the group gamma, you can generate a family by taking all subgroups of conjugates of K, or equivalently conjugates of subgroups of K. And that will be called F angle brackets K, the family generated by K. And once you have a family of subgroups, you can ask for a classifying space for that family. And the defining properties of a classifying space for a family of subgroups of gamma is that it's a gamma CW complex, which just means it's a CW complex with a gamma action which permutes the cells. It has isotropy in the family. So if you look at any given cell, the isotropy subgroup of that cell is in our family F. And it's kind of universal among spaces with isotropy in F, in the sense that any gamma CW complex with isotropy in F admits a unique gamma equivariant map into the classifying space up to gamma homotopy. And a proposition which is often attributed to Wolfgang Luke says that classifying spaces always exist and are unique. Well, I guess that follows from the defining properties that they're unique up to gamma homotopy type. And the most useful conditions for checking if something is a classifying space are, does it have isotropy in the family? And are the fixed point sets for each subgroup in the family contractible? So these two conditions tell you that you've got a classifying space. For example, I guess most people are familiar with the ordinary. So there's a kind of slightly confusing terminology. So the classifying space of the trivial family will be not B pi, not B gamma, sorry, but E gamma. So it will be a contractible space because we want the fixed set of the trivial subgroup to be contractible. So if the trivial subgroup is in the family, then the classifying space has to always be contractible. And saying that isotropy is in the family in this case means that we have a free action. So this is just going to be E pi in the usual sense. It's not hard to see that if you take the family of all subgroups, then a point with the trivial action will do as a classifying space. But the most interesting for us is this last example. So if you take the family of subgroups of gamma generated by a subgroup K, then you can take as a classifying space the infinite join of copies of the coset space gamma mod K with its obvious transitive gamma action. So this is a good source of classifying spaces. And as a special case of the final example, we look at the diagonal subgroup inside the Cartesian product pi times pi, and we let curly D be the family generated by the subgroup, the diagonal subgroup. Then one can show that the space of cosets of the diagonal subgroup is in bijection with pi itself, and the action by translation converts to the left-right action that we saw before. So actually I should say here, the infinite join E pi with the left-right action of pi cross pi I mentioned before is a model for the classifying space for the family generated by the diagonal subgroup. So you get the following proposition, which builds on the proposition of Michael I mentioned earlier, which says that TC pi is equal to the smallest k for which the map from E pi cross pi to this classifying space factors up to pi cross pi homotopy through the K skeleton of this classifying space. What do I mean by the map? Well, in general, because this is a free pi cross pi space, so its isotropy is all trivial, and the trivial group is contained in the family D, because we're taking all subconjugates of the diagonal. We have a uniquely defined map here. But also, I mean, we know that E pi, the infinite join of copies of pi, is a model for this classifying space. And there's an obvious equivariant map from E pi cross pi to E pi, which is just basically multiplication on pi, but with an inversion. Okay, so we previously characterized TC pi like this, but now, because this k plus one fold join is k dimensional, you can use equivariant cellular approximation to get a map to the k skeleton, and we also apply the equivariant Whitehead theorem. So we're replacing the k plus one fold join with the k skeleton, and we're replacing E pi with an arbitrary model for the classifying space. So what does this tell us? Well, if you define the geometric dimension of a group gamma with respect to a family F to be the smallest dimension of a classifying space for that family, then we see it follows in a straightforward way from the previous proposition that TC pi is bounded above by the geometric dimension of this family curly D. Because if you had a classifying space of dimension k, then certainly the map to it would factor through the k skeleton. So that's immediate. But we seem to have replaced a kind of difficult to get at topological characterization with an equally difficult to get at topological characterization. So we want to give algebraic bounds on this geometric dimension. And luckily that's been done, but it requires the theory of Bredon cohomology and Bredon modules over the orbit category. So I have to say a bit about that. So I took out all the pauses from my slides because I thought people might want to read them at their own pace, but now I'm kind of regretting it. Anyway, so take a family of subgroups of a group gamma. The orbit category is a category, the category whose objects are the orbits of an action with isotropy in F. In other words, the orbits are the coset spaces gamma mod H, where H runs over all the subgroups in the family. And the morphisms are just the gamma equivariant maps between such things. You can be more explicit about what the morphisms are, but I don't need to do that here in order just to state the results. And then a Bredon module is, or a module over the orbit category, is just a contravariant functor from the orbit category to abelian groups. And morphisms of Bredon modules are natural transformations of functors. Now, it's useful to point out here that if F is the trivial family consisting just of the trivial subgroup, then you get, as the orbit category, you get a category with one object and one morphism for each element of the group gamma. And you see then that a Bredon module is nothing but a module over the group ring of gamma. So this generalizes in a quite natural way modules over the group ring. And as you'll see, Bredon cohomology generalizes group cohomology. So you can show that these Bredon modules form an abelian category with enough projectives, whatever that might mean. It just means that we can do homological algebra in this category of modules in the way in which we're accustomed to doing if we ever do cohomology of groups. Because there is a trivial Bredon module constant z, which takes the value z on every object of the orbit category, and on every morphism is just the identity homomorphism. So then we define the cohomology of the group gamma with respect to the family F and with coefficients in a Bredon module M by taking X in the category of Bredon modules of the trivial module with M. So we have to find a projective resolution of the constant or the trivial module by Bredon modules, take hom of that resolution into M, and then take cohomology of the resulting thing. So although these modules over the orbit category are a bit unusual when you first see them, the method of defining cohomology is entirely familiar. And then the cohomological dimension of the group with respect to the family is just the largest degree in which you have non-trivial cohomology for some Bredon module. Now, one can show that if you have a classifying space for the family and you take its cellular chain complex, you obtain a projective, in fact, a free resolution of the trivial Bredon module. I'm sweeping some stuff under the rug here, actually. So each of these chain groups, to obtain a Bredon module, you need to take for each subgroup H, you need to take the chains on the H fixed points. But then you see in this way you obtain a functor from the orbit category. And I haven't told you what a free Bredon module is, but these will all be free Bredon modules. And so a projective resolution, a classifying space of dimension k is going to give you a projective resolution of length k. And therefore, you get that the cohomological dimension of the family is always bounded above by the geometric dimension of the family. And Luke and Meintrup, generalizing a result of Eilenberg-Ganea, showed that in fact you can always get a classifying space of dimension, the cohomological dimension, provided the cohomological dimension is at least 3. So these two things don't in general coincide, because in fact for certain families, I think for the family of finite subgroups, there are examples where we have geometric dimension 2 and cohomological dimension 2 and geometric dimension 3. So there are counterexamples to the Eilenberg-Ganea conjecture for general families. We'll come back to that later on in the talk. Okay, so putting together what we have so far, TC is bounded above by the geometric dimension of this family of subgroups of pi cross pi, which is bounded above by this algebraic quantity. How about lower bounds? We also have a lower bound. So whenever you have an inclusion of families, it induces a functor on orbit categories, and therefore it induces a restriction functor or natural transformation from cohomology with respect to the larger family to cohomology with respect to the smaller family. You also need to kind of restrict the Bredon module. So since we allow that the trivial group is in our family D, we have a restriction from the Bredon cohomology with respect to D to the ordinary group cohomology, which is just the Bredon cohomology with respect to the trivial family. And if you find a class in the ordinary group cohomology of degree k, which comes from, is the restriction of a Bredon cohomology class, then TC is greater than or equal to k. in actual fact, the class here, which comes from Bredon cohomology, will have TC weight K. So it contributes K to the lower bound. And well, this restriction map can actually be thought of geometrically as being induced by the map that we were talking about from E pi cross pi to the classifying space. And as we've seen, if TC is less than K, this map factors through the K-1 skeleton, so must vanish on K cohomology. This kind of lower bound has been utilized by Sasha in his proof that TC of a non-abelian hyperbolic group is the maximum it could be, so twice the cohomological dimension. So what he does is he finds a particular model for the classifying space of our family and shows that when you take the orbit spaces under the respective pi cross pi actions and look at the induced map, this map is non-trivial in ordinary cohomology with local coefficients in this degree. So somehow it's not using the full force of this Bredon cohomology, and if I had had more time before the talk, I would have checked whether or not the ordinary twisted cohomology can be thought of the orbit space, can always be thought of as an instance of Bredon cohomology, but I think yeah. So, I mean, you can sidestep using the Bredon cohomology and just use this fact about this map of classifying spaces. But I think perhaps using the full force of Bredon cohomology could lead to stronger results in some cases. I'll pause there, ask if there are any questions, because I have this, I anticipated a question. But if there are no questions, I'm still going to run out of time, so I'll just carry on. So this is now part 2. Were there any questions? I can only see Jesus's face, and he seems to understand. And now I can only see my co-authors' faces. Okay, seems there are no questions, so I will just push on. So this is part 2 about this more recent work on equivariant LS-category of groups. And I hope it will become clear that this work wouldn't have existed without the previous work. So just to recall, the equivariant Lupton-Schneermann category of a G-space X is the smallest K such that you can cover X by K+1 open and G-invariant sets, for which the inclusion is G homotopic into an orbit of the action. And this is a G homotopy invariant, and just as with the ordinary Lupton-Schneermann category, it provides a lower bound for the number of critical, in this case, critical orbits of G invariant functions in the case of a G manifold. So you can ask the same question that Eilenberg-Ganea asked about category and Michael asked about TC for the case of a group acted on by another group. So if pi is a discrete group and it's acted on by a group G by automorphisms, you can ask, well, first of all, you have to ask, what's the correct definition of the equivariant LS category of the group pi? And then you might ask, what's a description of that in terms of algebraic invariants? And I want to mention here, the reason I first asked myself these questions was because with Andres Angel, Helen Coleman, and John Oprea, we proved that the equivariant LS category of spaces is a Morita invariant for group actions, which, unwrapping that, means in particular that it satisfies 2 conditions. So if K is a normal subgroup of the group G, which acts freely on X when you restrict the action, then the equivariant category of the quotient group acting on the quotient space is just the same. So you quotient out the free normal action. And also there's this kind of induction property that if G is contained in H, then you can extend the action to an H action and obtain the same thing. So I was hoping that by looking at equivariant category of groups, we could obtain more example calculations where this could be used to calculate some new equivariant categories. As it turns out, I'm not sure that we can do that, at least for the first property, because the spaces that we end up taking the equivariant k-pi1s that we end up taking the equivariant category of are never free actions. So yeah. So anyway, so here's what seems to be the correct definition of the equivariant category of a group. So G is acting on pi, so we can form the semi-direct product of pi with G. Inside that semi-direct product, we have a copy of G, which is just the base of the semi-direct product. So it's just elements 1, G, where 1 is the identity element of pi. We look at the family generated by that G. So it's all subgroups of conjugates of the base in the semi-direct product. We observe that if we have a classifying space for this family, the normal subgroup pi in the semi-direct product intersects trivially with each of these conjugates of the base. And therefore, pi acts freely on this classifying space. So the orbit space is a nice, well-behaved CW complex. Also, because this classifying space is contractible and we have a free pi action, the orbit space is a k-pi1. But because we originally had an action of the semi-direct product, the action of G descends down to the action on this orbit space. So now we have an equivariant k-pi1. And because the classifying space we started with was unique up to pi semi-direct product G homotopy, the orbit space is unique up to G homotopy. So we get a unique G homotopy type of G equivariant k-pi1s. So that looks good. Also, from what's gone before, if I've got the family generated by G, if I take the coset space, I mod out the semi-direct product by G, I'm just going to get, as a set, I'm just going to get pi. And well, the action that you get on that pi is just going to be the action of G on pi. Okay, so well, it turns out that for various reasons, this seems to be the correct definition of the equivariant category of the group. And that's lucky because we know some stuff about this classifying spaces. And then you can show, using much the same method as we did for TC, that the equivariant category of the group is the smallest k, such that the map, well, this time it's the identity map on this classifying space, factors up to equivariant homotopy through the K skeleton. I could have written E pi here with its action of the semi-direct product. So pi acts on E pi, and so does G, and the actions are compatible. So we're in an even better situation than we were for TC, because now we've got the identity map rather than a map between two different spaces. So now if you define the equivariant geometric dimension of pi to be the geometric dimension of this family of the semi-direct product, and the equivariant cohomological dimension to be the cohomological dimension of this family, the semi-direct product, then you get this kind of Eilenberg-Ganea, but with a G, which says that, assuming G is finite and pi is discrete, you have this chain of inequalities. So I'm not sure whether the G finite is necessary. I used some results about equivariant sectional category, which are only have only been proved thus far for G compactly, to get this proposition. And then the furthermore says that if you have equivariant cohomological dimension 2, then the equivariant category is 2. That uses a little bit of equivariant obstruction theory. And again, the details there are only pinned down for G finite. Okay, but finite group actions are already interesting. So, yeah, so the equivariant category is almost always equal to the cohomological dimension, according to this. We haven't said anything about cohomological dimension 1 yet, but we were able to prove the equivariant version of the Stallings-Swan theorem. So Stallings and Swan proved that if a group has cohomological dimension 1, if and only if it's free, and that's easy to see that that's equivalent to having a one-dimensional classifying space. So we were able to do the same thing for these equivariant versions, at least in the case when the group acting is finite. So equivariant geometric dimension 1 is equivalent to equivariant category 1, is equivalent to equivariant cohomological dimension being 1. And all of these things are equivalent to the group being a non-trivial free group, but it also has to have a basis as a free group, which is permuted by G. And I should have put on the slides, but I didn't. If you take the integers, so an infinite cyclic group, with the action of Z mod 2, so the group with 2 elements, which is just the sign representation, then you can't find a free basis which is permuted by G. And in that case, the equivariant cohomological dimension will be infinite. So you really do need this extra condition to get dimension 1. So this was not straightforward to prove. We used extensively a version of Shapiro's lemma for Bredon cohomology to reduce to the classical Stallings-Swan result, and the following algebraic statement, which turns out to be kind of the most interesting part. So we all know that if the cohomological dimension of a finite group is infinite. However, if you take the cohomological dimension of a finite group with respect to a family of subgroups, it doesn't need to be infinite. It can be finite. But what we showed was that it cannot equal 1 in that case. And it was a little bit surprising that this wasn't known already to the experts, but it was kind of non-trivial to prove this. So there was a series of reductions, reduce it to the case of the family of all proper subgroups of a simple group. And then we reduced it to showing that the poset of proper subgroups of a simple group has cohomological dimension greater than 1, where to define the cohomology of a poset, you just take, instead of functors out of the orbit category, you take functors out of the poset. two abelian groups, and those are your modules, and then you have a more general notion of cohomological dimension. So we used a lemma of Cheng in a fairly obscure paper from the 70s, which characterizes when a poset has cohomological dimension 1. And there was a delicate argument with the subgroup structure of a finite simple group, which Udi was the one who came up with that, I must admit. Okay. Yeah, so as a corollary, if you have a discrete G group with G finite, all of these invariants coincide, except for the possibility that there might be a G group whose cohomological dimension and category are 2, but whose geometric dimension is 3. So this is the equivariant version of the Eilenberg-Ganea conjecture. And we currently think that such a group does exist, and that maybe the best Wiener-Brady examples, souped up to make them equivariant, could give could do this for us. Okay, so I think I've got enough time just to briefly do a mind dump. Some things that I thought of in the summer and then promptly forgot, and then tried to remember for this talk, which may lead nowhere, but maybe somebody has something to say. So given any group pi, it acts on itself by conjugation, and this is the adjoint action. So I'll use the notation add for this. Now, when you form the semi-direct product of the adjoint action, it turns out that the semi-direct product is isomorphic just to the ordinary Cartesian product of pi with itself. And here's an explicit isomorphism. G comma x goes to gx comma x. I'm not sure who originally observed this, but it's in a paper of Crabb and Sutherland about counting homotopy types of gauge groups. And the thing is, this isomorphism sends the family G generated by the base of the semi-direct product to the family D of diagonal subgroups, as is fairly easy to check. And so you can reframe the upper bound for topological complexity of a group as the cohomological dimension, the equivariant cohomological dimension of pi with respect to the adjoint action, which, provided the stuff that I said works for infinite groups as well as finite groups, which there may be some technicalities there, but I'm fairly sure it would work. This can be interpreted as the equivariant LS-category of the group pi. Now we've also got a lower bound given by the category of the group pi, or the category of the k pi 1 space. And that can be viewed as the equivariant category of pi acting on itself trivially. So intriguingly, we've got TC of the group is sandwiched between two equivariant categories of the group. So it's tempting to wonder whether there's some action between the trivial action and the conjugation action, for which we have TC of pi is the equivariant category of pi. And I haven't ruled that out yet. And then finally, I was quite pleased with myself that I finally managed to understand something about the fibrewise viewpoint, which has been employed with great success by Iwase and his collaborators, notably to give a short proof that the topological complexity of the Klein bottle is 4/5. So you can interpret, at least I learned this from a paper of the first 3 authors and a preprint of the final name here. So how I interpret what they did is that you have the adjoint action of pi on pi, and this is sort of, it induces an action on the infinite join of copies of pi, but also that descends to an action on the orbit spaces B pi and BK pi, because it's compatible with the action of pi on itself in such a way that this works. Then they show that TC pi is the smallest k for which there exists a fibrewise map of Borel constructions from the Borel construction of B pi on B pi to the Borel construction on BK pi. So this was the orbit space of the k+1 fold joint. And this is a map over B pi. And this has to do with equivariant classifying spaces and so on. So I got a bit excited when I understood this and thought maybe we can say something in terms of equivariant category. But it turns out that the existence of such a map is equivalent to a map from E pi cross B pi to BK pi, of a pi map from E pi cross B pi to BK pi. But then you kind of pass to the cover, and this is equivalent to there being a pi cross pi map from E pi cross E pi to EK pi, where this is the same or isomorphic to E pi cross pi. So it unravels to the original proposition of Michael. Okay, and that's all I had to say. So I'll stop there. Thank you.
Okay, if everyone would unmute their microphones, then we get to clap for. Are there any questions?
I have one question. Mark, if you can go back to the last slide in part 2 of your talk, you have this nice corollary that seems to be related to the situation, non-equivariant situation of the Ganea Eilenberg conjecture. I wonder if this version of your corollary is related to that, and if you would have some kind of relation to the Whitehead equivariant version of the Whitehead conjecture.
Oh yes, well that's a very interesting question. So firstly, if you remove all the G's, you have the non-equivariant situation exactly. So I mean, it's you have these equalities, and it's unknown whether there exists a group of CD2 and GD3. Now, non-equivariantly, you know that one of these two conjectures is false. So the Whitehead conjecture says that a subcomplex of an aspherical 2 complex is aspherical. And Bespina-Brady showed that you can't have both. So they produce something which is a counterexample to either Eilenberg-Ganea or Whitehead. Yes, I did think about this. What's the equivariant Whitehead conjecture? And whether or not, if we manage to prove that there's a counterexample to the equivariant Eilenberg-Ganea conjecture, well, I guess, yeah, that's a very good point. So you could formulate an equivariant Whitehead conjecture, which generalizes the ordinary conjecture. And I think you could probably show that one or the other of the equivariant ones must be false.
I think it would be interesting to try to generalize the geometric group methods in Bespina's approach to this example in the case of equivariant situation.
Yeah, so this is precisely the example we're looking at. So they take this this graph, which is the one skeleton of so you have a flag complex, which is the punctured Poincare sphere essentially, and it has an action of A5. So they take the right-angled arting group associated to the one skeleton of this thing, and take the kernel of the map which sends all the generators to 1 in the integers, and that's the Bespina-Brady group associated to this graph, and then they show that this thing has these curious properties, but they're not using the action of G. So our hope is that by building in the equivariance, which is there, we can get a counterexample. So we already show in our paper that that example has equivariant cohomological dimension 2. It's unknown whether its geometric dimension is 2 or 3, I believe, but we hope to show that its equivariant geometric dimension must be 3. But then, yeah, you have a very interesting point that this should be related to an equivariant Whitehead conjecture. So like a G subcomplex of a, well, I mean, actually there are various ways you could think to formulate that, so I won't try and do it on the fly. This is another thing which I thought about before lockdown and have promptly forgotten about. Yeah.
Thanks.
Any other questions?
I have a question. First, I want to thank Mark. Beautiful talk, very interesting. Thank you very much. And as results, new results are very impressive. You mentioned this result of Bredon and Bredon. I just wanted to comment on this. I mean, when we speak about the Whitehead conjecture, there are two different ways of understanding it. I mean, you can say, in general, a subcomplex of a spherical complex is a spherical. A spherical two-dimensional complex is a spherical. This is one way of stating it. But the other way is kind of restricted to finite spherical complexes. So a subcomplex of a finite aspherical simplicial complex or cell complex is a spherical. So these two versions are probably not equivalent. What Bredon and Bredon theorem says that if you take this full version of Whitehead conjecture and Eilenberg-Ganea conjectures, then one of these two is false, right? But it doesn't imply that this restricted version of Whitehead conjecture is false, because in their construction, they operate with infinite complexes. And in fact, if you look at models producing random aspherical finite simplicial complexes, in many models like this, both Eilenberg-Ganea and Whitehead conjectures are satisfied. It doesn't prove the deterministic version of Whitehead conjecture, but it still hints into this direction. Right. So this was one comment, but I also wanted to make a question or comment about your first part of your talk when you spoke about TC of pi, and you said that there is no even conjectural answer to this question. I think there is, well, I'm not sure, conjectural, so who knows, is it true or not? But remember, I mean, you didn't mention this, it's also in our paper, that canonical class and powers of canonical class, and also Bredon canonical class and its powers.
Yeah.
And I mean, actually this height of Bredon canonical class equals Bredon cohomological dimension, right? So, so maybe you can say something about this. What do you think about this?
Well, you perhaps are making a conjecture that the height of the Bredon canonical class is equal to TC.
Well, we know that height of Bredon cohomological class equals Bredon cohomological dimension. So if we believe in this, this will also imply that, yeah.
Okay, I did, you know, I said I prepared a secret slide, which if anyone asked, I would go to. I anticipated that someone might ask whether the upper and lower bounds that I talked about may coincide. This may be sort of tangentially related to your question, but I know that for a long time we believed that or we hoped that maybe the upper and lower bounds were the same. And well, I put we here, but I currently don't believe that they should be the same for the following reasons. So, I mean, here, CD, this notation means like the largest degree in which there's a class from this family which restricts non-trivially to this family. I didn't introduce this notation, but that's what we had for the lower bound. Now, we are talking about, so that TC of pi can be identified with the covering associated to the diagonal subgroup. Everything we did generalizes to the covering, to the sectional category of a covering of an arbitrary subgroup inclusion. In particular, we have that the sectional category of this covering of, well, BH, B pi means the classifying spaces, is bounded below by such a thing and above by such a thing. But you can easily cook up examples where this guy in the middle is finite, but this guy is infinite. So if you have H being normal in pi and the quotient group is finite, then this, and then if you have a normal subgroup of a group and you take the family generated by that, so it's basically just all subgroups of H, it's easy to show that the cohomological dimension with respect to that family is at least as big as the cohomological dimension of the quotient group. So if you have a normal subgroup inclusion where the quotient is finite, such as the pure braid group in the full braid group, which comes up in this Smale-Vasiliev work, you know, they're calculating the sectional category of the map from the ordered configuration space to the unordered. You can have that this guy is finite because it has because B gamma is finite dimensional and this guy is infinite. So for these reasons, I think, I mean, we're unlucky that the diagonal subgroup is not normal, but if it were, we wouldn't expect these two bounds to be the same. Yeah, I don't know if that answers your question as posed, but it's perhaps a useful observation to make.
Thank you.
Any other questions? Well, if not, thank you, Mark, again. That was a great talk. And let me remind everyone, you'll be receiving email messages about the next seminar. The next seminar is November 19th, and the speaker is Lucille Vandenbroek.